Our final presenter today is Mike McCullough, who will talk about a novel approach to the reduction of false positive and negative identifications in screening of pesticide residues in food analysis. Mike McCullough is a Strategic Technology Business Development Manager working for Waters Corporation within the Food and Environmental Vertical Market Group, having previously worked in the Pharmaceutical and Validation departments. Since joining Waters, he's had a keen interest in the use of time-of-flight technology and its application in many areas such as metabolite ID, impurity profiling, natural product profiling, and residue screening. His experience gained through external and internal collaborations has enabled Mike to contribute to the current ease of use available in mass spectrometry technology, including ion mobility mass spectrometry. And so, without further ado, I'll turn the presentation over to Mike McCullough. Mike?
Great. Thank you, David. Thanks for the introduction. I'd just like to say that the work presented here today has been performed in collaboration with Severin Goscinny and Vincent Hanot of WIVI-SP in Belgium. So, as an overview for the presentation, as a brief introduction, we'll look at the classification of screening and benefits of TOF screening. And we'll look at collision cross-section screening as a new identification point. And I'll introduce the collision cross-section screening software that's being used. We'll also see how that ion mobility can be used to perform routine screening and the benefits of spectral cleanup that can be obtained, as well as the unique proteomer identification. And then finally, I will give a summary of the presentation. So the area that we're going to focus on today really is the non-targeted suspect screening area using time-of-flight technology. Non-targeted relates to the acquisition type. And so we screen against a comprehensive library of known compounds, of which mostly standards are available. So what are the key drivers for accurate mass screening? Well, we have the ability to perform full spectral analysis, and this provides greater insight into the composition of a complex sample. And we have increased specificity in the complex matrices, so we have accurate mass for the precursor ions and the diagnostic fragment ions. And we're also able to perform non-targeted analysis. So we have the ability to measure compounds without the pre-requirement to tune up specifically for each compound. And also, we have the ability for a larger number of compounds to be screened for with their adducts because we're performing full spectral acquisition. And that's a far easier challenge compared to performing such assays using triple quadruple or tandem quadruple based screening methods. So the detection results that we typically use to reduce false detections, well, currently using the Waters TOF screening solution, we have a pesticide library that has over 2,000 compounds with both structures, synonyms, formulae, of which we have over 600 which have detection results. However, I should point out that the greater the size of the library, there is an increase in chance that you will get false detections. So we try to utilize information in the library where we have structure, retention time, accurate mass precursor ions, accurate mass fragment ions, isotope patterns, and isotope intensities to reduce those false detects. And today we're going to incorporate collision cross-section into that equation and into the library. So we're still going to apply tolerances such as plus or minus 2.5% and mass accuracies of less than 5 ppm. These are very stringent parameters, but you'll see later that actually we'll be able to make those tolerances a lot less tighter thanks to the use of collision cross-section generated from ion mobility. So what is collision cross-section? Well, we're going to utilize collision cross-section as a new identification point. And it comes from the heart of the SYNAPT G2S platform, or a SYNAPT-based platform. And the SYNAPT, as you can see here from the schematic, is actually a QTOF-based platform that at the heart of it has ion mobility separation. And the ion mobility separation performed is based on size, shape, and charge. And that separation gives you an orthogonal separation taking place to the UPLC separation taking place at the front of the end of the instrument. So what is CCS? Well, collision cross-section is an important distinguishing characteristic of an ion, which is related to the chemical structure and its 3D conformation. It's robust and it's a precise physiochemical property of an ion. So let's take a look at some data, some ion mobility data. What you see here is the extract of mandarin, a challenging matrix of which we've overlaid the UPLC separation. Orthogonal to that UPLC separation, we have ion mobility separation that you can see here from these white ion intensities. So under each chromatographic peak, well, these ions are orthogonally separated, but they're not chromatographically separated. And today we're going to use an example here in the center of boscalid, a pesticide of interest. And we're going to use that as the example to show some of the benefits of ion mobility. Let's take a look at that in the three-dimensional view. And our pesticide is there in the center, and we have the UPLC separation here, left to right, and then top to bottom, we have the orthogonal mobility separation. So you can clearly see how we get separation of the components orthogonal to the UPLC separation that you conventionally produce. Now, what are the benefits? Well, take a look here. We have the conventional MS spectrum, and in amongst there we have our pesticide boscalid. And here we've background subtracted the chromatographic peak that boscalid is a part of, and our ion of interest is here. As you can see, there are still a lot of other ions present in that spectrum. And why is that? Well, let's take a look at the actual extracted mass chromatograms for some of the matrix peaks and our peak boscalid. We can see that they're overlaid and we have little or no resolution at all. So it's not surprising that we can't actually generate a single component MS spectrum. However, if we look at the data within ion mobility, we can see that those matrix components and boscalid, our pesticide here, have been completely resolved. And that allows us to generate a single component MS spectrum. So in addition to the benefits of cleanup, we can now have a look at some other properties of ion mobility. And what we're going to look at here in a moment is the actual drift time that you can generate from ion mobility that will enable us to overcome some of the issues that we can see here on this slide. For boscalid here, we have an expected retention time of 7.35 minutes. However, with the four matrices, pear, mandarin, leek, and ginger, we can see that the percentage retention time error varies from 1.73 to 5.53%, which is well outside the acceptable of plus or minus 2.5%. But we'll see now here that actually we should be able to widen these tolerances using CCS or collision cross-section and drift time. So let's take a look at the drift time data, some drift time data. And what we've done here is overlay pesticides, their drift times in four matrices, mandarin, ginger, and leek. And we can see that the drift times of these particular pesticides are pretty much on top of each other, and there's very little variation. So statistically, we were then able to compare solvent standards compared to standards within matrix. And we could see that both the solvent standards and the pesticide standards in matrix belong to the same population. And we observed that there was a subtle deviation of just 2%. And that gives us the confidence that we can actually use CCS as an independent identification point. And it also clearly shows that actually collision cross-section is independent of the matrix. The drift time is independent of the matrix. So we can utilize ion mobility to produce an identification point. So let's take a look at the new ion mobility software, the Unify CCS Research Edition. I believe that collision cross-sections and ion mobility are going to break the mold of residue screening and change the way that people will perform residue screening in the future. So we'll take a look at some data, an approach here. And here we're going to cast the net wide. So rather than applying very tight tolerances, we're actually going to apply less stringent tolerances. So we want to catch everything. And then what we're going to do is actually apply intelligent targeted software filtering to find our target of interest. So here we have some results, and we have the results of a EU RL proficiency sample, FV13. And in here now in the software, we can see that actually we have the expected collision cross-section present, we have the observed collision cross-section, and the collision cross-section error. And in this sample, we're actually expecting to detect 8 residues. But actually, the results show that indeed we've actually observed 29. So how are we going to reduce that? Well, we have collision cross-section errors here, and we can see here greater than 2%. And we also have mass measurement errors here, and some of them greater than 5 ppm, the expected tolerance. So what we're going to do is we move to the next slide. This data was actually produced using 20 ppm mass measurement tolerance, 10% CCS tolerance, and also retention time tolerance of actually 1 minute. So they're far greater than those conventionally used. So as we now move to the next slide, we'll reduce those tolerances to 10 ppm and the presence of a diagnostic fragment ion. And we can see now that we've reduced our 29 to just 9, but we're still only expecting 8 to be detected. And what we have here are thiobendazole and isofenthos methyl. And we can see that isofenthos methyl has a collision cross-section of 3.49% error, and its mass accuracy is actually 0.5 ppm. And we have thiobendazole, its cross-section error is just 0.28%, and a mass measurement error of 7.68 ppm. And we were able to see actually that the slight offset in the mass measurement error here was due to ion statistics, and it's just 1.6 millidaltons at M/Z 202. But you would actually think that the correct identification here was isofenthos methyl. But if we apply a collision cross-section error tolerance, we're actually able to see that you would have indeed actually had 1 false positive and 1 false negative result. So let's apply that collision cross-section error. And we can see that with ion mobility that we actually have more specificity, confidence and efficiency. And we've removed 1 false positive and avoided 1 false negative. But ion mobility is not just about collision cross-section. It allows you to perform spectral cleanup as well, and that enables improved efficiency. And within the software, we're actually able to view the data in more than one way. We can view the data as conventional MS data, as you see here, or we can view it with the ion mobility separation that you've acquired activated. And we're again dealing with the same proficiency test sample, and here we're actually looking at spinosad and its precursor ion here, color-coded in green within the software. However, as you can see, there are a lot of other ions present. Now, interacting with the ion mobility separation here, we can simply resolve out those other background ions because they've now been ion mobility resolved out. Now, let's think about actually what we're acquiring here and what we're doing. We're actually performing UPLC separation, then we're performing ion mobility separation, and then we're actually performing fragmentation of those precursor ions that are actually ion mobility separated. And in this particular data set, there are over 52,000 components that have all been used to generate precursor ion and fragmentation ion data with accurate mass. So these fragments can now quickly be put into the scientific library because it's very clear to which fragment ions belong to the precursor ion. So we actually have drift time aligned fragmentation as well as retention time aligned fragmentation information. But it's not just about spectral cleanup or collision cross-section. Ion mobility, it gives you a unique data visibility, which again can improve efficiency in your analysis time. Let's take a look here again for the same proficiency test sample. We're going to look at indoxacarb, and we have one chromatographic peak. We have the extracted mass chromatogram for indoxacarb, and we have 2 extracted mass chromatograms here for the 2 diagnostic fragment peaks of indoxacarb, and that is equivalent to MRM transition type data. However, this one peak here that you see here is not everything that you think it is. There's more to it than meets the eye. And ion mobility makes that visible. So for the first time, and uniquely with the SYNAPT G2S, we've been able to see protomers. And protomers are different sites of protonation on the molecule. So we in fact actually have two data points that we can put information into the scientific library. And for these, we've been able to generate two collision cross-sections. So we can generate a collision cross-section with this protomer and this protomer. So that gives us two identification points. But it's not just the CCS that's important here. Let's take a look at the actual fragmentation spectra. We can actually see that for each protomer, we have different fragmentation pathways produced. Now that's absolutely critical when it comes to performing the analysis, because with protomers, their ratios will change depending on the conditions utilized, whether it be the capillary voltage, cone voltage, matrix, eluent flow rate, and pH. So if you're using MRM transition as a means of analysis, then if those protomers vary, then so will your diagnostic fragment ions. And that means that you could produce a response that is actually lower than it should be, and because the ratios of the diagnostic ions have actually changed, and therefore an exceedance may have been missed. But what's critical in this set of data here is that we can actually see that for each protomer we have two common fragment ions, and so using ion mobility we're able to actually see which diagnostic fragment ions we should use that would really make a very robust method of analysis for characterization and identification of indoxacarb. So just to summarize this particular section with indoxacarb, what we have accurate mass, precursor and fragments, we have spectral cleanup, we've shown retention time and drift time aligned data. We also have two protomers. In fact, we have three collision cross sections because we also had a sodiated adduct as well. So that gives us three identification points. And we also have two fragmentation routes. So we have a unique combination, all working together to give a very unique identification and solution. So it gives us unique confidence and efficiency, and that in itself is unique with ion mobility. So finally, to summarize, we've shown false positives can be removed and false negatives avoided using CCS values as a screening parameter. CCS can be used as a complementary identification point, and mobility resolution facilitates spectral cleanup for precursor ion fragmentation spectra. And so CCS, it adds confidence in the identification time, where in identification where retention time or mass shifts have been observed. And also we've shown uniquely that protomers that have never been observed before have been routinely identified and characterized. So, and I'd just like to say thank you to our collaborators Severin and Vincent at ISPWIV in Belgium, and over to David once again. Thanks very much.
Well, thank you, Mike, for that very informative presentation. We now have time for a few questions, and our first question, Mike, is, for ion mobility, how easy is it to set up, calibrate and configure my system so I can generate this extra dimension of data in my world?
Well, the short answer to that, David, is it's easy to set up, it's routine, but just let me explain a little more. To perform ion mobility separation and acquisitions, all system parameters are default and can be used with confidence, so it's only a case of selecting ion mobility mode when using the SYNAPT system. Otherwise, it operates just like a normal QTOF. So to generate CCS values, it's necessary to create a mobility calibration, which uses the same IntelliStart functionality that we currently use to create mass calibrations. So when you calibrate, you perform a mobility calibration at the same time as the mass calibration. After that, all the data generated can be processed to produce accurate mass and CCS values. And of course, the more experienced analysts can take advantage of the IMS parameters to adjust ion mobility resolution should they wish to do so.
Okay, and our next question is it possible to screen for unexpected known and unknown compounds using CCS as the primary parameter? Well,
first, in order to answer that question, I should say that when generating CCS data, we generate CCS values for all components detected. Hence, we do have CCS values for expected and unexpected compounds, whether they are known or unknown. So using Unify software, if the CCS value is known, that is, you're screening for an expected CCS value, then it would be possible to screen using CCS as the primary parameter. For example, using the software, it would be possible to detect all peaks, and if the analyte of interest had an expected CCS value of 90 angstroms, filters could be set to show only detected peaks with the expected CCS. And from there on, additional parameters such as the precursor ion and fragment ions could be applied to increase the specificity of the screening parameters. However, if an unexpected analyte is detected, the structural elucidation functionality of Unify can be used to make an identification, and then the unexpected identified component can be assigned to the scientific library. The assignment will contain the measured CCS value. This can then be incorporated into analysis method, and just remember that CCS values are generated for all the detected mass spectral peaks. Also, it's not always the case that something can be identified, and there are many applications or areas where it's required to determine that the same components are present, for example, comparing batches of a produced product. In this respect, remember that the substance does not have to be identified to be added to the scientific library, just named. Therefore, you could have a library of unknown compounds, and you can target in both previously and yet to be acquired data. For the unknowns, we could then name them, for example, unknown 1, unknown 2, unknown 3, etc. In this case, once again, having CCS as an additional identification point gives confidence that the same unknown component has been identified.
Okay, our next question is, does CCS count as an identification point?
Okay, David, well, to answer that question, we should consider the respective guidance and legislation for pesticide residue and veterinary drugs analysis. For pesticide residue screening, with respect to the guidance document, SANCO 12495/2011, the document states as follows. For a higher degree of confidence in identification, further evidence may be required. This can be achieved through additional mass spectrometric information, for example, evaluation of full scan spectra, additional accurate mass fragment ions, additional product ions in MSMS, or accurate mass product ions. If the isotope ratio of the ions or the chromatographic profile of isomers of the analyte is highly characteristic, it may provide sufficient evidence. Otherwise, additional evidence may be sought using a different chromatographic separation system and or different ionization techniques. And this is the key point, or any other means providing supporting information. So, also importantly, for the Commission Decision 2002/657/EU for veterinary drug residue analysis, the performance criteria for analytical methods is actually being reviewed and is in the process of being revised. It will also include the acceptance of further evidence to give a higher degree of confidence in identification. So CCS is a parameter that is being investigated. We are working with thought leaders that believe CCS can increase the specificity of identification and ultimately the confidence in assignment. So I think therefore CCS is a perfectly valid additional identification point to produce a higher degree of confidence in identification. It's something that should be considered as an option to improve efficiency in screening applications and reducing false detections. As I say, we are working with thought leaders that believe CCS can increase the specificity of identification, and CCS can now be determined routinely as a part of a screening workflow. So I believe it's a matter of time. It will be used routinely as an identification point.
Okay, our next question is, how does the measured CCS value differ from one SYNAPT instrument to another? Can we obtain CCS libraries which are transferable?
Well, another good question there. We are currently working on the feasibility of a CCS library for pesticides. So far, we've worked with a limited number, a couple of hundred, and we are characterizing adducts and any fragmentation that takes place. So we've been able to generate libraries on 5 instruments within a study incorporating instruments in the US, UK, and Belgium. And those individual libraries, we're typically able to obtain less than 2% variation in the CCS values. And in the majority of cases, the variation is actually less than 1%. So this has been achieved using a standard G2S acquisition format and does not incorporate recently introduced enhancements, one of which is the LOC CCS, which will further improve the precision and reproducibility of the measured CCS values. So with respect to the performance I've just discussed, I just would like to reiterate that the development work was performed using the standard G2S platform, and I have no doubt I'll improve upon these results in the coming months.
Okay, and I think the final question we have today, Mike, is what advantage does ion mobility and the CCS approach give over high resolution, for example, over 100K?
Well, David, we have some very unique advantages because we are uniquely resolving on size, shape, and charge. For example, there are advantages when dealing with isomers, conformers, and protomers, and in this case, no matter how much mass resolution you have, they won't be resolved. Where we have empirically isobaric species such as isomers, they can have different CCS values, which can be used to uniquely identify a specific isomer. Of course, this applies to the conformers and protomers also, and it has been shown in this presentation that the pesticide indoxacarb has 2 protomers. We've also seen this for spinosad and fenproximate, and I've no doubt we'll discover more since we've only worked with a limited number of pesticides. Being able to resolve isomers, conformers, and protomers allows the individual fragmentation spectra to be obtained, and these may well be unique. So in addition to that, remember, where 2 protomers exist, we have 2 CCS values. And these give 2 additional identification points. So we're given a very high degree of confidence in identification. With ion mobility, there is a high degree of specificity and the ability to obtain greater understanding of the assays being performed. Therefore, we have the opportunity to use ion mobility to produce more robust analytical assays. We have produced also unique data where we've been using ion mobility to understand the challenges of fluoroquinolones assays in the veterinary drugs residue world. And in this case, we've been using ion mobility protomer separations to achieve that. I also feel that I should point out that when an analyte is present at low levels and detected as just a monoisotopic peak, CCS gives an additional independent identification point with accurate mass, again, given a very high level of confidence even where no isotopic information exists.
Well, once again, Mike, thank you very much for that very interesting presentation. If any more questions do come in, I'm sure that Mike would be happy to respond to them by email afterwards.